In this video, I will derive the kinematic equations of classical mechanics in one dimension. This is something you generally learn in your basic physics in the first or second week of classical mechanics. And these are equations that essentially tell you how a system or an object moves over time. Namely, if you know the initial values of the position, the velocity, and you also know the acceleration, you're able to tell where the object will be at a certain time t later. Now, a premise here is that I will derive these equations in one dimension. What I derive here easily generalizes to 2 or 3 dimensions, and the reason for that is because the components of a vector decouple in the sense that they're independent of one another. So what's true in the x direction is also true in the y and the z direction. So there's no need to derive them in 3 dimensions. Also, if you're watching this video, I will assume that you know the definition of displacement, which in one dimension is given by x final minus x initial. You also know the definition of the average velocity, which is given by the change in displacement over the change in time. And you also know the definition of the average acceleration, which is given by the change in velocity over the change in time. This is all we need in order to derive the kinematic equations. Now, I want to make something clear here. I'm going to make a change of variables, or let's say I'm going to redefine delta t just to simplify the variables. So recall that delta t means t final minus t initial, where t final and t initial are the times at which you measure the beginning and the end, say, of the motion of a system. Now, generally, if you do things in a smart way, your t initial essentially represents physically the time when you start your stopwatch. But to make your life easier, you generally always start your stopwatch at the time 0 seconds. And therefore, we can just set t initial equal to 0. And by doing that, delta t will become just t final. But because we're not subtracting anything from t final, we can just call it t. And t will represent some time after your t initial, which is set equal to 0. This is done only to make the equations simpler when you do the derivations. Now, what I would also like to say here is that the derivation I'm going to present in this video is not going to be anything new. This is pretty standard. It's the way I teach it in my class, and it's also the derivation that you will find pretty much in every physics textbook, whether it's at the algebra level or at the college level. What I'm aiming to do in this video is to give you enough details so not only you learn what the kinematic equations are and when you use them, but hopefully you see why they have the form they do and where they come from. So let's get started. Let's start with this equation here. We have the equation for the average acceleration. And because we want to derive the kinematic equations that are generally found in textbooks, we're going to assume that the acceleration is a constant. Now, if you've taken physics, you might see why that's useful, because one example, for instance, where the acceleration is constant is where the acceleration is equal to g, for instance. Okay, so one example would be that when the acceleration is equal to g, the acceleration of gravity, which is 9.8 meters per second squared. Okay, so let's get started then. If we rewrite this equation here, we have delta v over t instead of delta t is equal to this acceleration. If I write this out, I get v final minus v initial over t is equal to a. Now the first thing I'm going to do is I'm going to multiply both sides by t so that the t cancels on the left, and I'm left with v final minus v initial is equal to at, and I can add v initial to both sides. And if I rewrite the equation, then I get v final is equal to v initial plus a times t. This is the first kinematic equation, and because I like to number the equations, I'm going to call this equation number 1. Now notice one important feature about this equation here. We're given that v final, the final velocity at some time t, is given in terms of the initial velocity and the acceleration and the time. That's precisely what I stated a couple of minutes ago, that the kinematic equations have the ability to tell you where a system will be and how fast that system or object will be moving at a later time t if you're given the initial conditions. The initial conditions in this case are given by the initial velocity and the acceleration, which, because it doesn't change, it's going to be constant throughout. So we obtain the first equation, which is the equation for the final velocity in terms of the initial velocity. Now, another important equation is the equation for the average velocity. Now, the average velocity can be calculated in a couple of ways. The simplest way of calculating the average velocity will be, if you know the initial and final values, you can add them and divide them by 2. This is exactly what you do if, say, you want to calculate your grade in a class, and the grade is based on 2, say, exam scores, and they have the same weight, they're worth 50% each. The way you do it is you add them together and divide by 2. So let's assume that we have v initial and v final. Then this will be a way of calculating the average velocity at which the system moves. But generally we're not given the final, because that's exactly why we derived equation number 1. But what can we do here? Well, we can plug in equation 1 into this new equation here and obtain also the average velocity only in terms of the initial velocity, the acceleration, and time. So let me show you what I mean. We have v initial plus, for v final, I'm going to plug v initial plus at, and it's all divided by 2. If I combine terms, I get 2 v initial plus at divided by 2, and then I can finally distribute that 2, so I get v initial plus 1/2 at. So this here is what I at least call my kinematic equation number 2. The number really doesn't matter. As long as you label them and you know which equation you're using and why you're using it, that's the only thing that matters in science. I always say this, science is not a collection of facts. It's a way of thinking. So what's important is that you know which equation to use when, and you also know why you're using a certain equation. So at this point we have 2 equations. We have one for the final velocity and one for the average velocity of the system. Well, we know that a system, when it moves a certain distance. So if we start at an initial position xi, it will be beneficial to calculate either the distance traveled or the displacement. So it will be beneficial, in order to calculate either the displacement or the distance traveled, to know both the initial and the final position. So our next equation will be one that allows us to solve for the final position. Now, if you go back, we have an equation for the average velocity, which is delta x over delta t. So we're going to play the same game here. We're going to rewrite this equation backwards. We're going to replace delta t with t, and we're going to write it like that. Okay, so what can we do here now? We're going to rewrite the left side. The left side is going to be x final minus x initial over t equals b average. So the first thing is we're going to multiply by t. So we get x final minus x initial is equal to v average times t. Okay, but recall, we always want to express the final values of the quantities in terms of the initial values. So for v average, we're going to plug in equation 2. So you see that my reasoning is sort of sequential here. We derive equation 1 and we use equation 1 to derive equation 2. Now we're going to use equation 2 to derive this next equation here. So I'm going to go to the next page and I'm going to have x final minus x initial is equal to v average times t. Now for v average, I'm going to plug in v initial plus 1/2 at all multiplied by t. And when I write it out, the right side becomes v initial t plus 1/2 at squared. The next thing I'm going to do is I'm going to add x initial to both sides. And so this equation becomes x final is equal to x initial plus v initial t plus 1/2 at squared. Now this is your third kinematic equation. So once again, notice that you have the x final here in terms of only the initial values, the acceleration, and time. That's always your goal. Okay? So now we have 3 equations, and these 3 equations have something in common. All of them, this equation here, and this equation here, and this equation here, all have in common that they include time, either linearly or quadratic. So these equations are good as long as you're given the time t. Or if you're not given the time t, you have to find t before you can use one of these equations here. But what if we want another equation that involves only the quantities x final, x initial, v final, v initial, and a, but no t? Can we find an equation like that where t is not needed? Well, we don't know, but maybe we can find out. But that would definitely be beneficial, because if you're in a problem, you're given only a combination of these quantities here, then you can use such an equation. So let's see if we can find this equation here. One way of solving for such an equation would be to combine 2 of those equations that we just derived, solve one of them for time, and then plug that value into the other one. So let's see. We have the one that we just derived. It's this one here. And we can pick another one. Let's say we pick the equation for the acceleration, which is v final minus v initial over t. And I'm going to solve the equation for the acceleration for the time and then plug it back into the equation for the position. So if I solve this equation here, I'm going to multiply both sides by t, and I'm going to divide both sides by a. The a cancels, the t cancels. So this equation here tells me that t is equal to v final minus v initial over a. Now, don't rush. Think about what you do. That's always important. Before you plug in the time, we're going to do the following. We're going to move back the x initial to the left, just because that does not involve time. And we're going to keep the 2 terms that involve time on the right. So we're going to rewrite this equation in the following way. And actually, we're going to now rewrite this as delta x. So we have here delta x is equal to v initial t plus 1/2 at squared. And now for time, we're going to plug in this thing here. So what do we get? We get delta x is equal to v initial, and then for t we have v final minus v initial over a plus 1/2 a, same quantity but squared. Now this is just an ugly equation that we can simplify by expanding everything. So let's do it. Sometimes you have to suffer in science. So the first term gives me a v initial times v final divided by a minus a v initial squared divided by a. And I did that by multiplying these two terms. That's squared. I almost forgot. The second term is a 1/2. Now notice that you have an a out here, and this one here, when squared, will be an a squared. So the net result will be a over a squared, which is 1 over a. So that tells me that each term in this expansion here is going to have an a in the denominator. So this is 1 over a, and then you get v final minus v initial quantity squared. Now before we move any further here, this difference of squares here, I want to remind you that if you have something like x plus y or minus y squared in algebra, this will be the first term squared plus the second term squared plus or minus, depending what you have, twice the product of the two terms. So for us, we would take the one with the minus because that's what we have there. So let's go ahead and write again the same expression on the next page. So we have delta x is equal to v initial v final over a minus v initial squared over a plus 1 over 2a, which is something I forgot here, times v final minus v initial squared. Based on what we just said, this is going to be v final squared plus v initial squared minus 2 v final v initial. Again, we can expand and we get v initial times v final over a minus v initial squared over a. And now you got to be careful here because each one of them gets multiplied by 1 over 2a. So you get v final squared over 2a plus v initial squared over 2a minus the 2 here and the 2 here cancel each other out. So it's minus v final v initial over a. Now we can clean this up a little bit because you have a lot of terms, but first of all, 2 of them cancel. Namely, the first one here and the last one are the same because v initial times v final is the same as v final times v initial. Multiplication is commutative, at least for numbers. So these 2 vanish. There are 2 other terms that look alike, this one and this one. One is negative, the other one is positive. They both have a v initial squared in the numerator, and there's an a and a 2a. So there are 2 ways of doing this now. Either you can multiply both sides by the common denominator and get rid of that denominator on the right, which I think is the best way of doing it, or combine those 2 terms above the green braces and then multiply by the common denominator. So let me rewrite one more step here, not including the 2 crossed out terms. And then let me tell you how I will do this. Okay, now you have the right side where I hope you guys all see that the common denominator is 2a. So in my opinion, the easiest way of doing this is to multiply both sides by 2a and then distribute that 2a on the right. So this gives you 2a delta x is equal to, if you multiply the first term by 2a, you get negative 2 v initial squared plus the second term becomes just v final squared, and the third term becomes just v initial squared. So it doesn't look too bad after all. There are only 3 terms, and now these two can be combined. It's negative 2 v initial plus v initial squared. So they combined give you a negative v initial. So this equation here is 2a delta x is equal to negative v initial squared plus v final squared. So we're almost done. Now I'm going to rewrite this equation by inverting the left and right side, which makes no difference. And then we're going to do one more step here. We have negative v initial squared plus v final squared is equal to 2a delta x. We're going to add the v initial squared on both sides. It cancels on the left, so finally we have v final squared is equal to v initial squared plus 2a delta x. And this is your fourth kinematic equation, also known as the equation without time, because as you notice here, this equation is the only equation that doesn't require time in order to solve for the final velocity. Now this is also useful because you can also solve for the displacement, because the delta x also appears. So this, in my opinion, is one of the most useful equations out of the 4, and you will learn, when you learn about energy, a much simpler way of deriving this equation just using conservation of energy. So now that we have all the equations, let's summarize. The 4 kinematic equations are v final is equal to v initial plus a t, v average is equal to v initial plus 1/2 at, x final is equal to x initial plus v initial t plus 1/2 at squared, and lastly v final squared is equal to v initial squared plus 2a delta x. I want to make a final remark here. I could have been more precise and give a subscript to all the velocities and the accelerations. Namely, I could have called each one of them x, 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 because we're dealing with the x direction. But because we're dealing with one dimension, it's obvious that all these quantities are along the x direction, so there's no need to clutter the equations even more. More importantly, you see that we have derived these for the x direction, but there's nothing special about the x direction. We could have as well derived these for the y direction or the z direction, because the derivation is not dependent on the direction that we pick. And therefore you can see why they're always derived in one dimension instead of 2 or 3, because if you want to obtain the equations for the y direction, all you have to do here is replace the x's with the y's, and the equations will have the same form. These are the only equations that you need in kinematics to determine the position of a system at a later time, given that you know the initial velocity, the initial position, and the acceleration. So I hope you guys found this video useful. Let me know what you think in the comments below, and I see you in the next video.